see how to apply the chain rule when the function has several variables. And each of the variables depends on one or more variables. So in this case, for instance, each of the variables depend actually on one variable. So in that case, we have that the composed function is going to be a function of one variable. At the end of the day, will depend only on t. So we can calculate just the total derivative of function respect to t, the only variable of the function. We could also call this z prime. So the derivative of z respect to t, or just the derivative of z, is going to be calculated by chain rule in this way, which means to calculate the partial of the function. Remember, this function is two variables, so the partial respect to x times the derivative of x. X is just a function of one variable, so this is no partial, this is just a regular derivative. And then the partial of z respect to y, and then multiplied by the derivative of y, which is just y prime. Okay, so let's see how to calculate these derivatives. So in this case, we have that our function is a function of two variables, and each of the variables depend on t. In this case, this one is t squared, and this one is 1 over t. Well, according with the formula that we just saw, we're going to need the derivatives of this function. So let's calculate those ones first. So the derivative of x is t squared will be just 2t. These are just regular derivatives, right? No partials. The derivative of 1 over t is minus 1 divided t squared. So these are the derivatives that we need to put in our formula to calculate the total derivative of z respect to t. And according to that formula, it's going to be equal to the partial derivative of z respect to x times x prime plus the partial derivative of z respect to y times y prime. So x prime and y prime, we just calculate them. Let's calculate now the partial derivatives of this function. So first we need here the partial of z respect to x. So this is going to be, see here that the function is a product. In both of the factors there are x, so we need to do the derivative of a product. So that will be the derivative of x, which is just 1, times the function, the second function as it is, and then plus the derivative, the first one just as it is, that will be x times the derivative of the other one, which is e to the xy, by the regular chain rule times y, which is the derivative of xy. Okay, so that is the partial derivative of z respect to x. And now times x prime, this is going to be just times 2t. And then we're going to add plus, and so here we're going to write the derivative of z respect to y. Observe that here, respect to y, the first of the functions is a constant now. So then this is not going to be product derivative, but because the constant will be just out. So it will be x times the derivative of e to the xy, which is itself times y. Sorry, x, right? So we are doing the derivative of xy respect to y is x. Okay, so then this is the derivative of z respect to y. And now this one times y prime that we already calculate, which is minus 1 divided t squared. Okay, and so now we do the multiplications here, so we can take common factors. You can see that these two things are common here, so let's take this as a common factor. So this will be equal to exy times, here will be 1, and here will be xy. So then this is 1 plus xy. And then times 2t plus, here we have x times x. Actually, it's going to be a minus, right? Because we have plus and minus here. So we can put here just minus. and so we are going to have here x squared e to the xy divided by t squared. So now we need to put the variables x and y as what they are, right? So x is t squared and y is 1 over t. So let's do this substitution. And so here will be xy will be t squared times 1 over t. So xy is actually t squared over t, which is just t. So then this in is et. 1 plus t times 2t minus x squared. So well, x squared is going to be t squared squared. So this is t to the fourth power. So t to the fourth power over t squared is going to be just t squared and et. Okay, put in now again common factor et. So we have inside here doing distributive, we're going to have here 2t plus 2t squared and then minus t squared. And then et, here 2t squared minus t squared is just t squared plus 2t. And then this will be the derivative of z respect to t, just the derivative of the function z that depends on t. So in this case that the two variables inside were depending on just t, just one variable. But these variables may depend on several variables also. So we can have a function, for instance, like this, of two variables, where each of the variables of the function depend actually on two variables, s and t. So at the end of the day, the composed function is going to depend on s and t. So in this case, we have to talk about partial derivatives. And we can calculate the partial derivative of the function f respect to s. And the way to calculate that will be to do the partial derivative of f respect to x. That is the same that before. I'm just using an alternative notation, right? But it is the same thing. The partial derivative respect to x. But now we multiply by the partial derivative of x respect to s. Instead of the total derivative, now we're going to multiply by the partial derivatives. And then we're going to do the derivative of f respect to y and the partial respect to s. Observe that when we are doing the derivative respect to s, the two partials that we take is respect to s. When we do respect to t, we're going to take the two partials of the variables respect to t. Okay, so for instance, on this function here, depending on two variables, and each of the variables depend on two variables too. In this case, the variables s and t. So we know that in the formula, what we need are all the partials of the intermediate variables. So let's calculate these partials first. So we have here that the partial of x respect to s is going to be just the derivative respect to s here is just 1, right? So 1. And the partial of x respect to t is going to be minus 1. Now, in this other one, we do here the partial of y respect to s, that is going to be 1, and the partial of y respect to t, that is going to be also 1. Okay, so now we're going to put them together in the formulas to calculate each of the partial derivatives, right? So for the partial derivative of f respect to s, so we are going to need the partial derivatives of f as before. So in this case, respect to x is going to be 2x times the partial respect to s, that is going to be 1. And then plus the derivative respect to y, that is 2y times the partial respect to s, that I erased but was 1 there. And then and that's it, right? So this will be 2x plus 2y. And then the derivative, the f respect to t, is going to be, again, 2x plus 2y. These are the same. But now we are going to multiply by the derivatives respect to t. that in this case are minus 1 and 1. So the partial derivative respect to t of the function f will be minus 2x plus 2y. And finally, we put that x and y what they are, right? So the last step is always that. So in this case, x is s minus t, so that will be s minus t plus 2, y is s plus t. Well, doing the operations here, we have 2s minus 2t plus 2s plus 2t. The t's cancel, and we have that this is just 4s. Doing the same thing here, you will get that the total thing here is 4t. And these are the two partials respect to s and respect to t, applying the chain rule. Of course, we can evaluate these derivatives are functions, so we can evaluate them at any point you want in the domain of the function. So, for instance, let's evaluate these functions at st equal, let's say, 3, 2, meaning s is 3 and t is 2. So, then this one, the partial derivative of f respect to s evaluated at 3, 2 is going to be equal to, which I substitute here, but 3, 2. So the only variable there is s, will be 4 times 3, that will be 12. And the derivative of f respect to t evaluated at the same point will be this one evaluated at 3, 2. Well, t is 2, so 4 times 2 will be 8. So that will be the evaluation of the derivatives at this particular point p equals 3, 2. As an application of the partial derivatives, we can calculate the derivatives of functions that are defined implicitly. I mean that we don't have the explicit formula of the function, but if they are defined implicitly, for instance, by an equation like this, so then we can calculate the derivative of the function as the quotient of the partial derivative of f respect to x over the partial derivative of f respect to y with a minus in front. So observe that we have here given a function of two variables that defines the function y as a function of x, but we don't have that function explicitly. We don't know y equal what is it. But if this function is defined by the equation of the f of x, y equals 0, so then we can calculate the derivative in this way, of course, when the denominator is not 0. Let's do an example with a particular function f of x, y equal y squared minus x squared minus sine of xy. And so let's suppose that y is defined implicitly as a function of y by this equation, y squared minus x squared minus sine of xy equals 0. So you see that we cannot even, in this case, we cannot even solve for y. It will be very complicated to get y equals something from here. But even without having the explicit definition of y, we can still calculate the derivative. So that is what this implicit differentiation is for. So we can calculate the derivative of this function y without knowing what the function y is. And according with the formula, this is calculated by doing this quotient between the partial derivatives. So let's calculate the partial derivatives of this function in this case. So the partial respect to x is going to be minus 2x minus cosine of xy times y. And the partial derivative respect to y is going to be equal to 2y minus the derivative of sine, again cosine, of xy now times x. Okay, and so now the only thing that remains is to put these functions in this way as a quotient there. So the derivative of y respect to x, right, the only variable, just the total derivative of x, we could also write y prime, is going to be equal to minus, and then we're going to write the derivative of f respect to x, which is this one here, which is then minus 2x minus y cosine. And this is going to be divided by the derivative respect to y, which is 2y minus x cosine. Let's do the multiplication. The multiplication of this minus by all the signs in the numerator, and the final result here will be then 2x plus y cosine divided by, and the denominator stay as it is, 2y minus x cosine of xy. So then this will be the derivative of y, even though we don't know what y looks like explicitly.